the way we did the dielectric case. Put it in. This region there is no current, so you can't put one there. But you can do anything you want out here. So we guess that for region 2, just the same thing we did with the dielectric problem. So I2 in terms of from I1, and to do that, at the interface. So what we did was to write down what the magnetic field would be here and here. And then look at the situation when we were right at the interface. So let me factor out an L out of each of these equations. And so what you'll get is on this side, once you do that, factor out a minus L on the top one and L on the bottom one, then all the integrals are the same. So again, we can cancel the integrals. So here we have I1 R over 4 pi. And then we have minus L plus I2R over 4 pi plus L equals mu 0 over mu I3R over 4 pi minus L. And so this gives us, we can factor out the R over 4 pi's and the L, so we get minus I1 plus I2 equals minus mu 0 over mu times I3. So now we put in for I3 what we found it to be up there, namely I1 plus I2. And so now we can solve for I2 in terms of I1. So you get I2 times 1 minus mu 0 over mu plus mu 0 over mu, bring it to this side, is equal to I1 times 1 minus mu 0 over mu. And therefore, I2 is I1 times 1 minus mu 0 over mu divided by 1 plus mu 0 over mu. Okay, so that gives us I2. And notice this is what we would expect. If mu was equal to mu 0, this would become 0, and it would be as though the plane wasn't there, which it wouldn't be. If mu was equal to mu 0, that's the vacuum situation. So then we can get I3 from up there. So it is I1 times 1 plus 1 minus mu 0 over mu, 1 plus mu 0 over mu. And so that'll be 1 plus mu 0 over mu, 1 minus, that gives you 2. Gives you 2 I1 over 1 plus mu 0. And if mu 0 over mu is 1, you get I1, so the field in the lower region is just what it would have been if there'd been nothing there. Okay with everybody? So it works out just the way it did when you had dielectrics. The arithmetic is slightly different, but the idea is exactly the same. But now what we want to do is to find the force on that current as a result of the plane. Now this is the aspect that we haven't talked about yet, so now we have to do that. We understood how to find forces between dipoles, but we haven't talked about forces between currents. So what we need to do is get the relationship that corresponded to the electric case. F was equal to Q times E. So the question is, we've done all this effort to find the magnetic fields. Now we have to ask, what forces do the magnetic fields exert on charges or currents? Okay? Now, that is an experimental question, and the result turns out to be, experimentally, that the magnetic field exerts forces only on moving charges. That B exerts a force not on Q, but on a moving charge. And the force that it exerts on a moving charge is QB cross B. Where up here it was QE, now it's QB cross B. And if you had a collection of charges in general, it would be for Q times V, charge times velocity, you would have a current times a little length. That would be a charge times a velocity, cross to B. So in general, if you have current loops, any sort of current, the force is the integral around the loop of I dl cross B. It's called the Lorentz force law. Now we could have used that as the definition of magnetic field had we chosen to. We chose to do it in terms of point charges or dipoles. Now, obviously, you can go from the equation for the force between dipoles to this. They're interchangeable. That's just some complex arithmetic, which I choose not to do. Amazing. I'm not doing one of these things. But this is the result. So, the complete story for electricity and magnetism is the four Maxwell equations, giving the divergence and the curl of E and B, and the force equation. And the force equation, then, is the sum of these two. So that the complete story for electricity and magnetism is F is Q times E plus B cross B. And so that's the force that's exerted. And now you couple that with the four Maxwell equations to give E and B, and you have the complete story. Okay? Now, what we then need to do is calculate the force exerted on the upper loop by the lower loop. Because we know the field at the top is the sum of the fields through the upper loop and the lower loop. We know that upper loop doesn't exert a force on itself. So all we really have to do is calculate the force between those two current loops using the equation I dl cross B. So that's what we need to do. Everybody following this? Okay, so that means the first thing we need to do is we need to figure out what is the magnetic field produced at loop 1 by loop 2. So first we'll calculate that. Okay? So let's erase this stuff. And we immediately recognize that that's trivial because we've already done it. We did it in the first part. When we got, to get B normal and H tangential, we had to calculate B produced by each of the little currents. So let's just go back and write down what we got for that force when we did it, for that field when we did it before. And the result we got was well, let's simplify life a little bit first. by the symmetry, what direction is the force going to be? It's going to be in the z direction, right? So all we really need to do is find the z component of everything. And so let's see how that's going to work out. We need IDL cross B. So here's our little current loop on the top. And here is the x-axis. Here's the y-axis, z-axis out of the board. And so when you're in some position, theta here, and this thing is R, the current is like that, I, and so IDL is I, and DL will be the length you go in a little distance d theta, which will be R d theta. But now, it'll have a component, as usual, in the x direction, which is minus the sine of theta, and in the y direction, which is the cosine of theta. So, IDL cross B will be IR d theta times minus x hat sine theta y hat cos theta crossed into bx x hat plus by y hat plus bzz hat. Okay? Now, that will be IR d theta times x cross x is 0, x cross y is z, so you get minus z hat sine theta times by. And then x cross minus x cross z is y hat sine theta dz. And y cross x is minus z hat cos theta dx. Y cross y is 0, y cross z is x, plus x hat cos theta dz. So, the z component of this, IDL cross B, the z component is just this one and that one. So it is minus sine theta dy plus cos theta dx. So, what we need when we set up this integral is by and bx. Okay with everybody? All right. Well, we found B due to current loop number 2 down here. And the B we found, let's go back to that. So the B we found was mu 0 I2R over 4 pi integral 0 to 2 pi d phi of x hat cos phi z plus L plus y hat sine phi z plus L plus c hat times r minus rho cos gamma minus b, and the whole thing divided by rho squared plus r squared minus 2 rho r cos gamma minus b plus c plus l squared to the 3 halves. And that's the result we got yesterday. So now we can write down bx and by. Now in our case, z is plus L, because that's the location of that upper current. So this becomes 2L. This becomes 2L. And this becomes 2L. Okay? So what's going to happen is that dx is going to be mu 0 I2 r over 4 pi. And here we'll just have 2L, factor outside. And we're left with the integral from 0 to 2 pi d phi cosine phi. Now, rho is r because the two loops have exactly the same radius. So this becomes r squared plus r squared minus 2r squared cos gamma minus phi, where gamma is the angle around the upper loop, the phi for the upper loop, plus 4 L squared to the 3 halves. And dy is going to be exactly the same thing. I2r 4 pi 2L, except we'll have a sine phi instead of a cosine phi over the same denominator. So that's by. Okay? Everybody's all right so far? Okay, so now all we got to do is put it into that thing. Now look what happens. You get sine, the theta now is going to be gamma because of just the way I label these things. So you're going to have sine gamma by, so that is sine gamma sine phi. Cos gamma cos phi, that's cos gamma cos phi. So that's cos cos plus sine sine, which is the cosine of the difference. Right? So the total force in the z direction is going to be mu 0 I r 2L divided by 4 pi integral, double integral, d theta d phi d gamma of cosine gamma minus phi divided by, let's factor out an r squared out of this thing, a 2r squared out of this thing. And so it'll come out as 2 to the 3 halves. The r squared will become r cubed. And then downstairs we will have 1 plus, I factored out a 2r squared, so this becomes 2 L over r squared. minus, factored out the 2, cosine gamma minus phi to the 3 halves. For both of these go from 0 to 2 pi. All right? Well, and then make a change of variables, let squiggle be equal to gamma minus phi. And so this complicated integral here, call that thing I, will become integral E goes from 0 to 2 pi. Squiggle goes from minus phi to 2 pi minus phi. And here we have d phi. Cos squiggle, d squiggle over 1 plus 2 L over r squared minus cos squiggle to the 3 halves. Okay, well this is just an integral over the period. So it doesn't matter whether I do it from this value to that or 0 to 2 pi. Because it's just a periodic function. As long as I go over the whole period, it doesn't matter what the limits are. So I can make this an integral from 0 to 2 pi. Well, once I've done that, then there is no phi dependence. And since there's no phi dependence, the integral over d phi would just be 2 pi. And so this whole thing will just be 2 pi times the integral from 0 to 2 pi. This is cos squiggle. Cos squiggle d squiggle over 1 plus 2 L over r squared minus cos squiggle to the 3 halves. And that's an integral you can do numerically as a function of L over r. Everybody okay? So putting that in for this, the 2 pi times the 2 cancels the 4 pi. And we have mu 0 times I2 and I1. I lost those things here. I1. So I1, I2. Now here we have 2 to the 3 halves. Okay. Now, I've got an r, which makes that an r squared, and I should have another r in here. Well, I lost an r somewhere, but the result is, I was not worried about the r. Write down what we got. Just putting all of those things together, what happens is you get where is it? Yeah, right here. So F turns out to be, it's all written out in your notes there, minus z hat mu 0 2 to the 3 halves L over R times I1 squared mu over mu 0 minus 1 u of mu 0 plus 1 times this integral, that thing, call this integral k, and then it becomes times k evaluated for L. Okay, let me just check, be sure that the arithmetic is right. Yes, that's correct. Okay, so that's the general result. You can calculate this for any value of L over R. I did it for you numerically for L over R equal to 2. And when you did it for 2, that integral is 0.01966, but I've written all that out for you. Okay. Now, can you think of a situation where we could have evaluated this analytically? Can you think of a limit that we know the result for? What do each of those current loops look like if you go a long ways away? What's a current loop when you're a long ways away from it? A magnetic dipole. So what this should be is the force between two magnetic dipoles. As long as L, the distance between them, 2L, is large compared to the radius of the loop. So what we ought to be able to do is take that integral over there, expand it for the situation where L over R is large, and end up with the force between two dipoles, which we've already worked out. Make sense to everybody? So let's ask what that integral becomes in the limit that L over R is large. So K goes when L over R is very much greater than 1. So let's see what will happen. Well, we'll have the integral from 0 to 2 pi cos squiggle. And now what we're going to do is factor out a 1 plus 2 L over R squared out of that thing in the denominator. So 1 plus 2 L squared over R squared. Now that'll come out as 3 halves. And we'll be left with 1 minus cos squiggle divided by 1 plus 2 L over R squared to the 3 halves. But now if this thing is, L over R is big, then this is small, so this is 1 plus x. And we know how to do that. 1 plus x to the n is 1 plus nx plus higher order terms. So we will expand this as that. And so this will become 1 plus 2 L squared over R squared, 3 halves, times integral 0 to 2 pi cos x times 1 minus, a minus makes a plus, 3 halves cos x over 1 plus 2 L squared over R squared dx. But what's the integral of cosec from 0 to 2 pi? 0. Right? It's a complete cycle. And the other one is the integral of cosine squared. Well, the average value of cosine squared is a half. Go from 0 to 2 pi, and you just get pi. And so this whole thing becomes pi 1 plus 2 L squared over R squared to the 3 halves times 1 times 3 halves for this thing. 1 plus 2 L squared over R squared. Okay, now we're making L over R very big. And so with L over R very big, we throw away the 1. And so this is 2 L squared over R squared to the 3 halves. And so we get pi times 3 halves, 2 to the 3 halves, 5 halves, 2 to the 5 halves. And then we have L squared over R squared to the 5 halves means L squared over R squared to the 5th, which is R to the 5th over L to the 5th. So the final predicted result is that F should be minus C hat mu 0 2 to the 3 halves L over R times I1 squared mu over mu 0 minus 1 mu over mu 0 plus 1 times this thing pi 3 halves R to the 5th 2 to the 5 halves L to the 5th. Okay, so that's the predicted answer. Okay, now what is that? Well, this and this makes that an R to the 4th over L to the 4th. And so we get minus Z hat mu 0 R to the 4th over L to the 4th. And then you have mu over mu 0 minus 1 mu over mu 0 plus 1 2 to the 3 halves 2 to the 5 halves, that's 2 to the 8 halves, that's 2 to the 4th, that's 16, so that's 3 over 32. So that is the predicted force in the limit that they're far apart. But we've already worked out what that force was. We did that earlier. We found the force between two dipoles. And it would have been, when they're lined up the way these are, it would have been attractive. It was mu 0 over 4 pi times 6 times the dipole of the first, the dipole of the second, over the distance between them to the 4th power. Now, L is, that's the distance between them, with a 2 in here. And if you put in our values for M1 and M2, it will match exactly. So that we have a check to see that things have, that we've done everything correctly, that reduces to the proper limits. And I worked that all out on the notes for you. Okay, that makes sense to everybody?
A little harder today.
It was a little harder today. That's why I wrote out the notes, so you didn't have to worry about it. I did the notes in great detail and pretty carefully, so it should be easy. Okay. Now, remember we did the experiment the other day, or did the calculation for what force ought to be required to separate, a plate from a bar magnet. And so today we're just going to try that. And so what do we get? About 17 or 18? What do you think it is?
15 or so.
15. Yeah, maybe 16, something like that. Now, we did the calculation. When I took a magnetization of 2 times 10 to the 6th. Now, for these magnets, the magnetization is approximately, it's 10 to the 6th over, let's see, we got a table here for what the magnetization is for these things. And it is about 10 to the minus 4 divided by 4 pi. Okay, what they've got here is the residual induction. And so you end up with the thing completely aligned. B in the magnet turned out to be 10 to the 4th Gauss. Now, the MKS unit is not the Gauss, it's 10 to the minus 4 of that. And so this is about 1 in the MKS units. It's about 1.
What are MKS units?
They're called Oersteds. And the units would be
I was with Adam when we were trying to come up with this for you. We were having a real difficult time finding magnetization.
Yeah, what he was able to look up, at least the chart he gave me here, was B. Now, it's not exactly what we want, but we can get an estimate of M from that. Because we know that B is mu 0 times H plus M. And the main contribution to B is M. H enters into it, but the main contribution is M. So M is a little bit less than B over mu 0. And B is about 1. Mu 0 is 4 pi 10 to the minus 7. And so this is 10 to the 7 over 4 pi, and that's a little bit less than 10 to the 6th. So maybe something of the order of 8 times 10 to the 5th. Now we're going to be a little bit smaller than that because we've ignored H. And remember, the result turned out to be proportional to M squared. And we had used M as 2 times 10 to the 6th. So we have maybe 2 over a point, well, let's say 0.5 to allow for everything. So that's 4 squared is a factor of 16. And we had estimated that it would be 400 newtons. And now we're going to divide by 16, and that gives us about 18 or 19. And we measured
The first time it did almost get right.
It almost made 18. So to the crudeness of which we're able to do this, we get the results we expected to get. Yes.
Well, just sitting there, it's a little under 2,
Yeah,
so
that's
it's
yeah,
the,
that's the gravity.
yeah.
Yeah, so we got to subtract 2.
So he also, he was able to measure the Gauss of the, both of the magnets, so if you wanted to use the magnets, he thought maybe you could use that, because he has those two measures.
What does this one turn out to be?
That was about 60.
It should be very similar.
It's going less and less. He had to like re-magnetize those
Yeah.
a couple times. It's like they're, oh, that was up to 17.
Call from Lydia Reddick.
Which I guess would be 16.
Can't even make the stupid thing quit.
Try the side button.
No,
That works
it turns the power off here. You're supposed to be able to just push decline. It should have stopped it.
When mine's
I think
in
you
my
just gotta
pocket-
press it harder.
You gotta press harder. Crush it.
When mine's in my pocket and it's going and I want to silence it really quick, I just squeeze it.
Yeah, you got a Samsung? This is an LG. It works a
So
little
that's
different.
bad.
Okay, so next time, so that's what we want to do with static electricity and magnetism. Now, next time, we're going to start doing the interesting stuff. And the interesting stuff is when we have time-dependent processes. And that's going to lead to light, electromagnetic radiation, inductors, AC circuits, the really interesting part of this. So on Friday, we're going to start time-dependent.